Hello everyone, I'm Renyuan Peng of Fudan University. I will introduce our work, Translating Images to Road Network, a non-autoregressive sequence-to-sequence approach. Here comes the contents of my presentation. First, I will briefly introduce the topic. Next, I will provide a detailed introduction to the method we have proposed. Our approach has undergone several stages of refinement and optimization. I will divide the explanation into three parts. Finally, I will demonstrate the effectiveness of our approach. Online road perception is of significant importance in autonomous driving due to its cost-effectiveness and real-time capabilities. Road networks comprise road landmark locations, centerline curve shapes, and road topological connection, effectively representing road structure information. Our work encodes the road network as a sequence and uses 6 front-view camera images as input to predict the road network sequence, enabling road network extraction. Then I will introduce our autoregressive method. Here comes the pipeline of sequence construction. First, we use a directed acyclic graph to store road network information, where nodes represent landmarks and edges represent centerlines connecting these landmarks. And for nodes with more than one parent node, we duplicate their parent nodes to transform the DAG into directed forest, ensuring that each node has a unique parent. Then we perform a depth-first traversal of the tree, thus obtaining an ordered node sequence. In the end, we represent each node using a 6-tuple. The framework employs a bird's eye view encoder to transform features from the front view image into the BEV plane. Subsequently, a transformer decoder sequentially generates tokens for the target sequence, guided by both previous tokens and the encoded BEV features. Autoregressive method can achieve road network extraction with significantly better results than previous methods. However, it has slow inference speed and cannot meet the real-time requirement of autonomous driving. To accelerate inference speed, we have designed a semi-autoregressive method. The objective is to divide the trees in the directed forest into smaller subtrees as much as possible, so that each tree will be simultaneously inferred and the autoregressive length can be reduced. Using key points as routes, identified by distinct visual features, such as starting points and branching points, the directed graph is transformed into several subtrees. The transformation and sorting rules are similar to autoregressive method, resulting in subsequences. We construct a two-dimensional semi-autoregressive road network sequence, where autoregressive prediction occurs within subsequences, and parallel prediction happens between subsequences. To accommodate the adjusted sequence, we have designed the following model structure. After projecting the features from the front view images onto the bird's eye view, we first employ a structure similar to DTR to detect key points on the BEV features. These detected key points are then flattened and used as prompts. Then we utilize a two-dimensional transformer structure to predict the subsequences. While the semi-autoregressive method improves performance and increases inference speed, it still requires a relatively long inference time. Therefore, we propose a fully non-autoregressive generation model, which can output the entire sequence at once. During training, we employ masked language modeling strategy. In inference, we take a fully masked sequence as input and iteratively mask the predicted token with low confidence. Here shows the visualization results on nuisance validation set. All three methods predict high-quality road network. Only slight errors occur when predicting landmarks locations for autoregressive and non-autoregressive methods. This is qualitative comparison on nuisance dataset with previous works. Our model demonstrates an advantage in both landmark location and connection. We use the precision recall and F1 score of landmark and reachability to evaluate the location accuracy of landmarks and the connectivity and accuracy of paths between landmarks. The two tables on the right display quantitative results. The results demonstrate the superiority of the proposed approaches compared to existing state-of-art alternatives. The above comprises the entirety of my presentation. Thank you for your attention.